Okay, so today we're going to finish, we're going to start section 6.5, rational equations and problem solving. So some of the objectives we're going to work on today are solving an equation containing rational expression for a variable. So basically we're going to say, here's an equation. I'd like you to solve for the given variable or for the designated variable. Solve number of problems by writing equations containing rational expressions, solve problems modeled by proportion, solve problems modeled by work, and solve problems modeled by different distance, rate times time. So this is probably going to be the hardest one right here. These ones aren't so bad. I just have to show you a little bit of a technique on how to work on those, but the distance equals rate times time problem will definitely be the harder sets. So let's first look at some steps to solving equations for a specified variable. Clear the equation of fractions or rational expressions by multiplying each side of the equation by the least common denominator, or the LCD of all denominators. So a lot of times we'll be dealing with rational equations. So we call this clearing the fraction. So, and again, most of the time in general, we do not like, you do not like to have the variable that you're trying to solve for in the denominator. So one method is just to multiply both sides by that variable to get it out of the denominator. Use a distributive property to remove grouping symbols such as parentheses. Okay, that's pretty standard. Combine like terms on each side of the equation. Once again, pretty standard. Use the addition property of equality to rewrite the equation as an equivalent equation with terms containing a specified variable on one side and all other terms on the other side. So this is basically isolate the variable. This is something you already know how to do. So don't freak out. This is just a lot of wording for basically saying isolate the variable. Use the distributive property and the multiplication property of equality to get the specified variable alone. Again, all of this is basically for that purpose, to isolate. So let me just show you an example of what we're saying here. So we're given that 1 over a plus 1 over b equals 1 over x. So we have an equation and we want to solve for a. So a is in the denominator. So we go back up here and we see that it says clearing the fraction. So multiply by the LCD. So what is the least common denominator between 1 over a, 1 over b, and 1 over x? Well, the LCD equals a, b, x, right? If you just, that is where all three of those can be multiplied together, and they'll all meet at ABX. So what I'm going to do is I'm going to write 1 over a plus 1 over b equals 1 over x, and I'm going to multiply both sides by the LCD, ABX over 1, ABX over 1. And then we're going to distribute that, okay? So when we distribute, now again, you don't have to write this out every time, but what you're really doing is you're doing ABX over a, ABX over 1 times 1 over a plus ABX over 1 times 1 over b equals 1 over x times ABX over 1. That's what the distributive property does. So everybody gets an ABX to multiply by, okay? So now let's do a little bit of canceling. So this a will cancel with this a. This b will cancel with this b. And this x will cancel with this x. So we've cleared the fraction. So now we're going to end up with bx plus ax equals ab. Okay. So what this has now done is we cleared the fraction. We no longer have to worry about fractions. However, we still need to solve for a. And the problem is we have a on both sides. So what we want to do, let's go over here, is we want to put a on one side of the equation. So what I'm going to do is I'm going to move everything to the right that has an a. So I'm going to subtract ax, subtract ax. Now notice we're left with bx equals ab minus ax. And I could not put those together because they're not actually like terms. Yes, they both have an a, but it's a b and an x. Those are different variables. So remember, combining like terms, you must have same powers and same variables. So we do not have that situation. However, I do notice that they both have an a in common, so I can factor that. So I have bx equals to a times b minus x. And again, I know I'm right because I could distribute the a back and I would get the exact same thing as I had before. So I know this works and I'm allowed to do this. And now I only have a single a, so I'm going to divide both sides by b minus x, b minus x. So I end up with bx over b minus x equals a, and I solved for my variable, okay? So that's how you can solve for a variable when you have three fractions. And this is a pretty, I don't want to say difficult problem, but this is one of the harder variety for solving for variables. A lot of them are a little bit easier than this. I feel that this step going from here to here is the hardest step in this problem. Multiplying by the LCD is what you have to recognize will help you with this problem. So those are two kind of keys, is recognizing that the LCD is going to help you. And then also realizing that when you have two A's on the same side, or two M's or two G's or two X's, whatever it may be, you can factor that out to get the X or the A or whatever variable as only one, and then divide by the extras. Okay, so there's that problem. Okay. Now let's switch to words. Okay, so instead of just a straightforward variable problem, we're going to now switch to a word problem, and we're going to try to translate it. So it says the quotient of a number and 9 times its reciprocal is 1. Find the number. So we have to think about this. What is the reciprocal of a number? So the reciprocal, so the reciprocal of a number means, you know, the not the inverse, but the flip of it, right? Whenever we say the flip, we really mean mathematically the reciprocal. So that's how we get this 1 over n, because if the number is n, then the reciprocal would be 1 over n, okay? Or if the number was g, then the reciprocal would be 1 over g, okay? So this is how we can think of reciprocals. So that's one terminology or one wording that we now understand. So what we're going to do here is we're going to kind of have the, how can I say this? We know that the quotient means division. We know that a number is n. We could call it x as well. And 9 times its reciprocal. Well, we know this is multiplying, right? And we know is equal sign, okay? So now down here, we have this all kind of typed out real nice. A number, boom. The quotient means division. And 9 times its reciprocal. So 9 times the reciprocal of a number is equal to 1. So now that we have this, this is our new equation, okay? So you have to know the wording and how to set things up. This is something that requires practice. So, you know, there might be a few in the homework that you're kind of struggling with, you know, feel free to come talk to me about those. So here you go, let's try this, all right? So first things first, let's rewrite it, n divided by 9 over n, right? Because 9 times 1 over n is the same as 9 over n equals 1. We know that division can be changed to multiplication. So we're going to have n times n over 9 equals 1. Okay, now hold on real quick. Let me catch up in my notes. All right, so now we end up with, what would that be? N squared over 9 equals 1. And we know to get rid of a 9 in the bottom, we multiply both sides by n. I mean by 9 over 1. So this would cancel, become 1. So now we end up with n squared equals 9. And again, we know how to get rid of a squared. We square root both sides. So this will become plus or minus. So we're going to end up with n equals plus or minus 3. So n equals 3 and n equals negative 3. And those would be our two answers. In the homework, it may ask you to do it like this, right? Remember, they like you to write it as a set. So n equals, and then they'll say the set of negative 3 comma 3. That's how they may ask you to write it. But again, this is just another technique that we can use to solve for a given variable or a desired variable. And again, you could check, this is just a check to say that we could plug these values in. We could say that the number n is in fact worth plus or minus 3, and we plug them in both situations, plus 3 and minus 3, and we get truth in both cases. We get 3 divided by 3, which is equal to 1, we know, and then negative 3 divided by 3, which is equal to 1. So 1 equals 1 is a true statement. All right, so now let's talk about proportions. A ratio is the quotient of two numbers or two quantities. So you guys know this is like A over B or 1 over X, you know, so on and so on. Now, a proportion is a mathematical statement that two ratios are equal. So this would be A over B equals 1 over X, or we could do A over M equals, you know, G over H. You can do whatever you want as long as you have this situation where you have one ratio equal to another ratio. A rate is a ratio of two different quantities, okay? So when you're talking about ratios in general, you're talking about things that are the same type of thing, okay? But when you go to a rate, you're talking about, you could say, you know, I'm going 7 miles per 1 hour, right? So we're dealing with two types of things. We're dealing with miles and hours. We're dealing with distance and time. So that's what they mean by, that's just a little distinction that they want to make for that particular situation, okay? So something that's really important for proportions is we have a proportion right here is cross multiplication. So cross multiplication, not cross canceling, says you're allowed to do A times D. So this would be A times D is equal to B times C. Notice that's what they're saying there. So this is something very powerful in proportions. And this is why we love to write a lot of things as a proportion, because it allows us to solve in a different way. So when we have a proportion, you always should have this in your back pocket. This is something that you can use, you know, countless times in a proportion problem. It's very, very helpful to know your cross multiplication or your cross product, okay? So let's look at this. A 170-pound person weighs approximately 65 pounds on Mars. How much does a 9,000-pound satellite weigh? Okay, so let's take a look at that. Okay, so let's write it as they have it. Okay, so there's a lot of ways you could do it. You could do it where you could do the pounds on Earth versus the pounds on Mars. So what I'm going to do is I'm going to do it that way first. 170 pounds on Earth versus 9,000 pounds on Earth. Okay, so I'm doing the two Earth weights equals, now I'm going to do the two Mars weights. Okay, so 65. So we know that the 170 weighs 65 pounds on Mars, divided by, now we don't know how much the satellite would weigh, X pounds on Mars. So I set up a proportion here that has Earth pounds versus Earth pounds and Mars pounds versus Mars pounds, okay? So I can now do my cross multiplying, okay? And technically, if you want to think about it, you could just say, well, these labels are going to cancel, but let's not worry about the labels so much at this moment. Let's talk, because I don't want to do all the writing. So this is saying 170 times X equals 65 times 9,000. Okay, so when we do this, we get 170x equals, and then 65 times 9,000. If you take out your calculator, we get a 585,000. Okay, now we know to solve, we just do 170 divided by 170. This cancels and becomes 1. And we're left with x equals, and then this is, let's take out our calculator real quick. 585,000 divided by 170. So I get 3,000, let's say approximately, let's round off. I get 3,441, let's say 0.1, let's say 0.176. However, The problem, in this particular problem, everything is in terms of pounds. They don't have decimals. So, or in terms of whole pounds. So I'm going to say that we're going to round up to 3,441 pounds. Okay, so that would be our answer for that particular problem. And again, when you're doing the homework, make sure you double check how they want it rounded. Now, I wanted to show you, I could have done it a different way. So that's the nice thing about proportions, is normally there's not only one way to do it. Let's do it exactly how they said. Let's do 170 pounds to pounds, so pounds a person to pounds on Mars. So I'm going to do 170. I'll just write pounds on Earth, just so we can save writing time, to 65 pounds on Mars. So notice the left-hand side is Earth to Mars. So then the other side, I have to do Earth to Mars. I must follow the way I set up the proportion. Okay, so now 175 to 65. So now let's do the satellite. It's 9,000 to, let me see, the satellite is 9,000 pounds on Earth. And how many pounds on Mars would it be? We don't know. So once again, I'm going to cross multiply. So we'll get 170x equals 9,000 times 65, which is 170x equals 585,000, which is the exact same problem we just did. Let's do some cleanup. So we end up with x equals, and then we can say we already know this because we've already done it, 3,441 pounds. Okay, so this would be 3,441 pounds on Mars. Okay, so notice two completely different proportions, but we still get the same answer. So remember, with proportions, it's all about the setup. Make sure that you follow how you're setting up your proportion on both sides of the equal sign. If you do Earth to Mars, then the other side has to be Earth to Mars. If you do Earth to Earth, then you have to go, person to satellite. Then over on the other side, you got to go person to satellite on Mars. Okay, so you follow your proportion. All right. So let's take a look at this next one. To estimate the number of people in Jackson population of 50,000 who have the flu shot, 250 people were polled. Of those polled, 26 had the flu shot. How many people in the city might we expect to have a flu shot? So this is a little bit of a stretch for statistics. So we'll just try to do our best with proportions. So we're going to do total population divided by polled population. And remember, this is just one way we can set up the proportion. And then we'll do, since we did total to polled, we'll do total flu to polled flu. Okay, so flu shot, let's say shot. Okay, so what we're going to do is we're going to plug in the things that we know. So we know the total population of 50,000 divided by the total, or the polled population. Okay, so the polled population was 250 people. And this is now going to equal total flu shots. That's what we're trying to figure out. We don't know how many people we would estimate have the total flu shot, or how many total people have the flu shot, versus polled flu shot. So the polled flu shot, we know that 26 had the flu shot. So now I'm going to once again do my cross multiply. So I now have 50,000 times 26, and that equals 250x. We're going to divide both sides by 250 to solve for x. So we should get, let me see, when we use our calculator, we should get 5,200 equals x. So that means we estimate there are 5,200 people. Oops. That have the flu shot. Okay. That's how many we would expect to have the flu shot in this population. Okay. So that's one way we can use proportions. Okay. So this is a different type of problem with proportion, but we have to set it up in a very specific way. These are problems that we talk about involving work. Okay. So it says an experienced roofer can roof a house in 26 hours. A beginner roofer needs 39 hours to do the same job, which makes sense, right? They're not as good at the job. So how long will it take the two roofers working together? So by using the times for each roofer to complete the job alone, we can figure out their corresponding work rates in portion of the job done per hour. So this is what I like to do. I like to always do it in terms of one, just because one is easy to work with. So that's also what your book likes to do as well. So what we're going to do is we're going to say, well, we're going to say this roofer in 1 hour, the experienced roofer can do the job. He'll have 1/26th of the job done, right? Because if it takes him 26 hours and he works for 1 hour, he has 1/26th of the job done. Just like if he had worked for 13 hours, he would have 1/2 of the job done, okay? Now, the beginner roofer can do it in 39 hours. So after 1 hour, he will have 1/39th of the job done. Okay. Now the thing is these people are not working against each other. In that case, we would subtract their times or their rates, but they're working together. So what we're going to do is we're going to add their effort. Okay. So now, if they're working together, how much of the job is done in 1 hour? 1/T. Okay. So if we come over here, if we come over here and look, it says, since the rate of the two roofers working together would be equal to the sum of the rates of the two workers independently, we have this equation. So the book and I work the same on these problems. So now what we're going to do is we're going to multiply by the LCD. So we need to think about where will 26, 39, and T all meet. Well, we know that 39 times 2 is 78. And 26 times 3 is 78. So we know that the LCD, and the way I did that, by the way, guys, is I just looked at 39 and I just said, when will 26 meet at 39? Well, it can't meet at 39. So then what's the next 39? It's 72, or I'm sorry, 78. So can a 26 become a 78? If the answer is yes, then that's my LCD between those two. So then I also have to incorporate the T. So I'm going to say 78T is my LCD. Okay, so I'm going to multiply everything by 78T over 1, 78T over 1. So now I know that the 26 and the 78 are going to cancel, and this is going to become 3T plus, now I know the 39 and the 78, remember I'm distributing, the 78T and the 39 is going to become 2T. Now, oops, did I write this as 78 over T? Sorry about that. It's going to be 78T over 1. I apologize. Please fix that in your notes. So then the T's will cancel and we'll be left with 78. So let's just solve this. This becomes 5T equals 78. Let's divide both sides by 5. And now we have T equals, and then 78 over 5. Let me get out my calculator. Oops. 78 over 5 is approximately, or is 15.6 hours. Okay, so that's how long it would take if they work together. So one guy can do it, one roofer, so guy or girl, a roofer could do it in 26. If they're experienced, they can do it in 26 hours. A beginner roofer can do it in 39 hours, but if they work together, they can do it in approximately or in 15.6 hours based on their work rates. Okay. So that's a pretty standard problem you guys will see. Sometimes they use like water pumps pumping into a pool. What if you have one water pump pumping in and one, somebody left the drain open? How fast is the water draining? How long would it take? That's a problem where you would subtract. So just be careful of how the wording is set up, okay? So another problem is distance equals rate times time problems. So distance equals rate times time problems are probably the most difficult in this section, I would say. So you guys have used distance equals rate times time in your life. You know that if you drive at 60 miles per hour for 2 hours, you'll drive 120 miles, right? So you know how to use distance equals rate times time. So whenever we start talking about problems that use distance, rate, and time, this is the formula you should be thinking about. Now, the formula can be solved for different variables. If I divide both sides by r, I get distance over rate equals time. If I divide both sides by time, I get distance over time equals rate. So these are other versions of the formula, right? So here's the base formula, but this is also the same formula, and this is also the same formula, just depending on which letter you need to isolate. Okay. So it says the speed of lazy river's current is 5 miles per hour. A boat travels 20 miles downstream in the same amount of time traveling 10 miles upstream. Find the speed of the boat in still water. So the key for us when you see these types of problems is we have to locate the speed of the current. We have to locate the speed downstream. We have to locate the speed upstream. But another thing we need to think about, oh, and also they want the speed. What's the final answer? They want in still water if there were no current. So how fast is the boat going? But then here's the big one. This is the one that people read right past. Same time, in the same amount of time. So that means they're both traveling for the same number of hours. Okay. So whether you're going upstream or downstream, you're traveling the same amount of time. That'll come back into play with these problems. Okay. So real quick. So right here it says we note that the rate of the boat downstream would be a rate in still water plus the current. So imagine if you're swimming and something's pushing you along. Let's say you swim at 7 miles an hour and something is pushing you along also with its speed of 10 miles per hour, then you're actually going 17 miles per hour. Think about like at airports when you get on those little moving walkways. If you walk your normal speed plus the speed of the walkway, then you're flying past people. It looks like you're running because you're combining your speed plus the walkway speed. That's the same thing with the current or with wind resistance in airplanes. So with the current, if the current's pushing you at 5 miles per hour and you were going 20, then you're now going 25. If the current's working against you because you're going upstream, then if you were going 20, you're only going 15, okay, in miles per hour or knots, whatever they're measuring it as. Okay. So, and this one will be in miles per hour. Okay. So here's a nice little way they set it up. So downstream, they have it set up as 20 miles with a rate of R plus 5, because if you're going downstream, the current is working with you. So time would equal distance over rate. Here we have upstream 10 miles, a rate of R minus 5, because whatever the rate of our boat is, minus 5 miles an hour. And then if we divided those two, we would get 10 over R minus 5. Since the problem states that the time to travel downstream was the same as the travel upstream, so this must be a spell check in the wording it. So this is upstream. We get the equation. So here's what we're going to do. We know that distance equals rate times time, okay? But the fact that they said the same amount of time means that both of them equal the same time. So I'm going to solve distance over rate equals to time. I'm going to solve for time. So for the first one, we know that it's 20 divided by R plus 5. Remember, this is just me saying distance over rate, okay? And not just the rate of the boat, but the rate of the boat plus the current, okay? Now this we know equals some time, okay? And then this is our upstream. I'm sorry, downstream. Sorry about that. This is downstream, right? Now let's do upstream. We know that that's going to be 10 divided by R minus 5. And that will also equal T because they both equal the same amount of time. Well, if this equals T and this equals T, doesn't that mean that they both have to equal each other? So what I'm going to do is I'm going to say 20 over R plus 5 has to equal 10 over R minus 5. So it's kind of like we cut out the middleman. They both meet at T, right? They both equal T. So then that means we're going to say they're both equal to each other. Now what we get to use is we get to use our cross multiplication because this is in fact a proportion, okay? So let's cross multiply. 20 times R minus 5 equals 10 times R plus 5. Okay, so now let's distribute. And let's see what we get. So this would be 20R minus 100 equals 10R plus 50. Let's solve for R. So I'm going to subtract 10R over to here, and let's add 100 over to here. So we end up with 10R equals 150. Now we know we can divide by 10. We can divide by 10. Come over here. We now have R equals, what is that, 15? 15 miles per hour. So we know that the speed of the boat would be 15 miles per hour. Okay, so that's what this is telling us, is the speed of the boat is in fact 15 miles per hour. Okay, and that's in still water. All right. So please let me know if you struggle with any of the homework problems. Feel free to meet up with me. And again, we could also check this. I forgot that there's a check. We could then plug 15 in. If we plug 15 in here and here, we end up with 20 over 20 equals 10 over 10. And we know this is 1 equals to 1, right? Check. Okay, so it does, in fact, the boat in still water is in fact 15 miles per hour. Okay, so there's more than just one type of distance equals rate times time problem, but a lot of the ones we're going to deal with, because this is a section on proportion, they are going to talk about the same amount of time. So make sure you key in on that and then set up your proportion accordingly. So please let me know if you have any trouble with the homework, and this will be the last video before our exam. All right, thanks for watching, you guys.